Hi everyone, we are Team Polaris 12345 and this video is about the Wobble Arm. The purpose of the Wobble Arm is to pick up the Wobble goal in an autonomous and endgame so we can get a total of 70 points with the Wobble. That is a great amount of points, so we decided to make a Wobble Arm. Description of the parts here. The green arrow is pointing at the servo, the blue arrow is pointing at the claw pincer, the red arrow is pointing at the bevel gear, and the yellow arrow is pointing at the frame. To be a little more in depth, the servo is used to close and open the pincer to get a hold on the wobble ball. The claw pincer is used to grab the wobble so that the robot can move it, and the bevel gear is used to increase torque to lift up and hold the wobble goal in air. So here are some of the motors and gears we used. So here's the motor we used initially. A rev correction motor that has 32.63 kgcm amount of stall torque. Moving on, we use a worm gear with a Gobilda 520200020003 motor that has 1620 RPM and the stall torque is 5.4 kgcm. The worm gear has a gear ratio of 24:1. To find out the total amount of RPM and stall torque the wobble is having, by combining the worm gear and the motor, we need to use a formula. To find the total RPM, which is rotations per minute, we need to divide the motor RPM by the worm gear ratio. The answer to that is 67.5, so the calculations are 1620 as the motor RPM and 24 as the gear ratio, so we divide 1620 by 24 to get 67.5 total RPM. Now for the stall torque, we get 129.6, which we get from multiplying the stall torque, which is 5.4 times 24, which is the worm gear ratio. The next and latest wobble gear and motor, with the Gobilda 520200020051 117 RPM motor. The bevel gear has a ratio of 2:1, and the new Gobilda motor has 170 RPM and 24.7 kgcm amount of stall torque. Now the RPM may seem less than the other motor, but actually when you calculate the total RPM, you get 58.5 RPM using the same formula. Total stall torque is 136.8, which is in the middle of the two old motors. Now we are going to compare all the motors to see why this current motor is better than the old ones. As you can see here, there is a table comparing the total wobble load from the different motors and gears we used. Also, the Rev Cortex motor did not have any gear, the RPM and torque are directly from the motor specs without using any formula. About the table now and about the stall torque, the Rev Cortex motor has a low amount of torque and did not really have the perfect amount of torque. Next, the worm gear with the 1620 RPM motor has a great amount of torque, but it had problems, such as it was stuttering a lot. Our last option is the bevel gear with the 117 RPM motor, and that has a great amount of stall torque, perfect to lift the wobble. Now moving on to the RPM, the Rev Cortex motor has the highest amount of RPM, but the efficiency is not about high and low, but it also depends on the torque value, which is low for the Rev motor. The worm gear has a good amount of RPM, but the stall torque was not great. The bevel gear motor has the lowest amount of RPM, but all the power the motor is giving goes to stall torque. Therefore, the bevel gear and the Gobilda 520200020051 117 RPM and gear is the best combo. Here are the claws and pincers we used. Initially, we used a simple one, claw and arm to grab the wobble. This design is simple, but has a lot of problems. First, you can see the red arrow, which is the direction of force of the wobble tilting because of gravity, turns the servo shaft front and back, even though the servo can only go left and right. The shear force on the wobble damages the servo shaft, that is no good. So our next design had to not put any force on the servo shaft and more on the frame. Here's our new pincer we're currently using. Our new pincer, it has all we need. Not to damage the servo shaft, but to put force on the frame. Our design uses gears to operate two arms at once without any twists on the servo. Since the force is still there, shown in the second image, it will not damage the swivel because the gear will take the force and the gears will separate, saving the servo shaft. To prevent the gears from taking the force, we mounted two plates tightly so that if the gear bends, it will bend with the gears, but the plates are tightly connected to the frame so that it will put pressure on the frame.